All right, guys. Hope you're all doing well. Back at you with the next lecture video here for Chapter 4, which is lecture video number 2. We're going to spend some time this class talking more specifically about subatomic particles. Now, I know we spent the last chunk in video lecture number 1 talking about kind of the history behind the atom, right, and kind of talking about where it came from its humble beginnings, all the way talking about with Democritus and his idea, right, of this indivisible small particle called the atom, all the way up to our most recent talk about the wave mechanical model, right, the modern model that we talk about, that scientists kind of refer to these days. So, talking about the atom, well, what is it that an atom consists of, right? And we kind of have a few ideas based on our last conversation, but atoms consist of 3 main things, and these 3 main things are called subatomic particles. Subatomic. Now, atomic meaning the size of an atom, right? So atoms are very, very, very tiny, right? Obviously, we can't see them with the human eye. So these are very, very small particles, these atoms. Now, subatomic, sub meaning even smaller, right? Sub or below or even smaller. So these particles here, protons, neutrons, and electrons, are even smaller than one single atom because there's a whole ton of these protons, neutrons, and electrons packed inside of one single atom. So let's get down to it, okay? Atoms are composed of the following subatomic particles: protons, neutrons, and electrons. An atom has a positively charged nucleus or center containing protons and neutrons, and then that positively charged center, the nucleus, is surrounded by electrons. So in the dead center is your nucleus. Inside of your nucleus are protons and neutrons. You can actually really quickly go back to this Bohr model here, right? Notice how in the dead center of this Bohr model is this right here, right? This is your nucleus. It's got protons and neutrons in it. Everything else around it are going to be your electrons, okay? So keep that in mind going forward here. If we go back to where we're at, there we go. All right, now, when we look at a couple of these things in this table here, let's go left to right. We've got particles, symbols, location in terms of where it's located in the atom, that's relative charge, because that's going to become important as we progress through this school year, and its relative mass in a new unit called AMU. And AMU just basically stands for atomic mass unit. Okay, atomic mass unit. Now, going from left to right here with them in specific is the proton. The proton has a lowercase p as its symbol. The location of it is the nucleus, like I've been mentioning, and it has a relative charge of +1. Okay, so one proton has a charge of +1. If you had 2 protons present in an atom, that will mean those 2 protons, 1 plus 1 is 2. So the positive 2 charge will be present on that. If you've got a total of 10 protons, it's 10 times +1, so positive 10. And then its relative mass is 1 AMU. So for every 1 proton you have, it weighs 1 AMU. Neutrons are not all that different, right? Neutrons have a lowercase n symbol. They are also located in the nucleus. But one of the biggest changes, one of the biggest differences between protons and neutrons are its relative charge, okay? No matter how many neutrons you could have 1, you could have 10, you could have 100 neutrons. They're all individually going to carry a relative charge of 0. So therefore, it doesn't matter how many you have, how many neutrons you have, they all are going to collectively have an overall charge of 0. They don't hold any charge at all, okay? Not like protons in any way. But one of the ways that they are like protons is that they do have a relative mass similar to them, which is 1 AMU. Next up, and lastly here are electrons. And electrons are arguably probably one of the most important ones. They're one of the subatomic particles that we talk about the most in the entire school year. So let's take a quick look. So electrons have a symbol that is a E with a minus sign. So E with a minus sign. Their location is not in the nucleus, just like the previous 2, right? Protons and neutrons are present inside of the literal nucleus, whereas the electron is located around the nucleus or inside of those electron clouds, those orbitals we talked about in the previous lecture video. Now, similar to protons is that they do have a charge, right? Electrons do have a relative charge. This time, though, electrons are actually negatively charged. They have a -1 charge. So similar to protons, where if I had 10 protons, my overall charge would be +10. If I have 10 electrons, well, you guessed it, my overall charge would be minus 10 or negative 10 this time, right? So it's always the number of electrons you have times -1, right? That gets you your number of electrons. One big drastic difference between electrons versus protons and neutrons is that electrons are actually virtually massless, right? When I say massless, they have next to no mass, practically zero. So their mass is so small and tiny and insignificant that you could have millions and millions and millions and trillions of electrons, but the mass of them collectively is actually so small that they're almost practically zero. Okay, so the mass of an electron is really not important. It's almost negligible. Now, onto atomic number. This is where we start to break down some of the things that you guys see on your periodic table, right? So if you have your reference table with you or nearby, you can take a look at this. The little symbol, I guess like the little thing on the top right-hand corner here is exactly the same setup that you have on your periodic table as well. So it's a good reference point to make sure that you're always looking at the proper things. The very first thing we're going to look at, though, here is the atomic number. And when you look at the periodic table, the atomic number is the bolded number in the bottom left-hand corner, right? So if we look, bottom left-hand corner is the bolded number here, which is atomic number, right? That's going to be the case for every single one of our numbers on the periodic table. Now, the atomic number tells you something about the specific atom of that element, right? It tells you exactly the number of protons in an atom. So if we look at this example here of carbon here, which has the symbol of C, right? If it has an atomic number of 6, that just means it has 6 protons. Atomic number of 6, number of protons, same exact thing, okay? So each element has a different number of protons and therefore a different atomic number. So as you progressively look at all, so if you grab your reference table here and you look at your reference table, right here on the periodic table, it has carbon having exactly 6 protons, right? Because it has an atomic number of 6. But if we go back one towards boron, boron has an atomic number of 5 because boron and its atoms only have 5 protons in it. Right, atomic number of 5, 5 protons, right? So whatever the atomic number is of your element for that particular atom, it's got that same number of protons, okay? Now, not only that, right, not only does your atomic number give you your number of protons, but it also gives you your nuclear charge. Now, this is where this idea of charge comes into play that we saw in the previous slide here, right? Again, if protons have a relative charge of +1, and I've got some atom that has 10 protons in it, well, 10 times +1 is an overall nuclear charge of +10, okay? Now, looking at that in terms of our carbon atom, for example, carbon has an atomic number of 6, which means it has 6 protons, but it also has a charge, or a nuclear charge of +6. Now, one important distinction here, guys, is that when we look at nuclear charge requires a plus sign or plus symbol in front of the number, because that's going to indicate the actual charge of the nucleus. So atomic number is just simply going to be 6. Number of protons is just simply going to be 6. Nuclear charge has to include the positive symbol, right? So if I write this down, atomic number is 6, number of protons is 6. But how you designate nuclear charge is not just with a 6, but with a +6, okay? So it's really important you make that distinction because if a question asks you for nuclear charge and you leave off the plus sign here, it's not going to be correct. Okay, so we have to make sure we make that distinction properly. All right, on to our next thing here, which is mass number. Is a little bit different. Now, if you look at the periodic table, and specifically at the key at the top here, okay, this key is always designated for carbon here. If you look at the periodic table, the top left-hand corner of it, and I'll actually go back a slide here, right? If we look at the top left-hand corner of the periodic table for any of our elements here, in specific, we're talking about carbon, right? We've got this right here. Top left-hand corner is atomic mass, and the atomic mass of carbon is designated to be 12.011. Now, atomic mass is very different than mass number. Atomic mass, mass number. They sound very similar, right? They both have the word mass in it. But mass number and atomic mass are very different things. So I am currently speaking to just mass number for right now. So mass number in specific is equal to the sum of protons and neutrons in an atom. If we go back and look at this chart here, guys, the only two of our 3 subatomic particles that actually have any mass here, relative mass, are our protons and our neutrons, right? So those are the only ones that are going to actually have a mass to give this this atom here. Okay, and they are written after the name of the element with a dash here, right? So for example, if carbon has a mass number of 12, it's going to be written as carbon-12. If we're going to have nitrogen, for example, right, nitrogen has a mass of 14, a mass number 14. It's going to be nitrogen-14, right? 14 is the mass number for nitrogen, 12 is the mass number for carbon, right? And it's a very, very basic calculation, right? Mass number equals number of protons plus number of neutrons, and that's it, okay? That's it. So you're just adding your number of protons to your number of neutrons, right? All right, continue the other half of this conversation, which is atomic mass. Okay, atomic mass, again, not the same as mass number. Mass number is one thing, which is your number of protons plus your number of neutrons. Atomic mass is something entirely different, and we're going to focus on this a lot more next class. But let's, as a brief kind of rundown here, atomic mass is how much, on average, one atom of a given element weighs in AMU specifically. Okay, now, atomic mass is what you guys see, and I mentioned this briefly, it is what you guys see on the periodic table, right? So if you look here at carbon on the periodic table, right, you look at the key on the periodic table, the top left-hand corner has the atomic mass, not the mass number, the atomic mass. Again, they're very different things. Now, and I have a little section here, which you guys are probably finishing up writing in here. Atomic mass is not always the same as mass number, okay? They're not always the same. Sometimes they're pretty darn similar, right? But oftentimes they are not, okay? So, for example, although it is often that carbon, on average, is going to have a mass number of 12 here, 12.011 is pretty darn close as an atomic mass compared to the mass number. And again, they're very, very close, right? 12 and 12.011, right? And they're relatively the same, right? Barring a couple of decimal places there. But again, they are not exactly the same. And we're going to get into next class why that is the case.